Good morning, everyone. We are Team 23, and today we are presenting our analysis on the discrepancies between the ERA5 climate reanalysis model and actual ground truth data from weather stations in France. Our goal is to quantify where and why the model fails. We started by establishing a baseline. Here, you see the probability density of the temperature differences. The key takeaway is this shift to the right. The mean difference is approximately 1.5 degrees Celsius. This tells us that, on average, the ERA5 model systematically underestimates the real temperature. We then asked, is this error random? The map shows it is not. While we see outliers in mountainous regions like Embrun, likely due to altitude relief issues, we noticed a significant pattern. To isolate the most interesting phenomenon, we made a strategic decision. We filtered the dataset to low-altitude stations to focus specifically on the urban heat island effect, recompare to weather stations. Is colder than reality. This brings us to vegetation. We used NDVI as a proxy for urbanization. On this chart, the left side represents urban areas, low vegetation, and the right represents rural areas. You can clearly see that the error variability, the size of the box, is much higher in urban areas. The model struggles to capture the heterogeneity of city and microclimates, whereas it performs much more consistently in rural, vegetated environments. Geographically, the model displays systematic errors. Inland regions exhibit a mean bias of positive 2.11 degrees, with a high RMSE of 3.32. By comparison, coastal areas are significantly more accurate. We see a similar trend with altitude. Low elevation zones show a peak bias of positive 2.29 degrees. This confirms that ERA5 mathematically fails to capture the heat amplification specific to low-lying urban environments. This seasonal trend is confirmed here. The bias follows a perfect curve, peaking in summer at over 2.5 degrees Celsius. ERA5 creates a smooth grid that fails to capture the intense localized warming of French cities during the summer, while the gap narrows significantly in winter. Finally, we attempted to model this error. The scatter plot confirms a negative correlation. As vegetation, NDVI, increases, the error decreases. Our recommendation is clear. To fix the ERA5 dataset for local applications, quantitative metrics must account for vegetation cover. A simple bias correction is not enough. We need a correction factor that varies with both season and urban density. To conclude, we move from simple observation to a statistical explanation. On the left, our model ranks the drivers of the error. We found that coastal proximity and vegetation, NDVI, are the strongest predictors of ERA5 bias. But the chart on the right reveals a critical limitation. We tested if adding vegetation data actually fixes the model. Look at the blue line. At high altitudes, it works perfectly. Adding vegetation data drastically improves accuracy. Now look at the red line. In low-altitude urban areas, the line is flat. The improvement is near zero. Conclusion: the urban heat island effect is nonlinear. Simply adding vegetation metrics is not enough to fix ERA5 in cities. We need complex metrics that account for 3D urban geometry,